Hello, class! I hope you all have a better understanding of vectors now. One of my favorite sections in physics is projectile motion. When you think about it carefully, projectile motion is a motion in two dimensions. An object launched in the air at an angle is moving in the x direction and the y direction at the same time. Here's a closer look of an example to what I mean by an object moving in the x direction and y direction at the same time. In this example, the ball is rolling off the table and another ball is dropped from the edge of the table at the same time. The solid green arrows you see at each snapshot of the ball shows the direction of the ball's path, and the length represents the magnitude of the ball's velocity. Notice how the magnitude of the velocity increases because of acceleration due to gravity. Now let's focus on the dashed green arrows for the x direction only. The velocity in the x direction is only represented for the ball rolling off the table because the ball drop has no motion in the x direction. Take a closer look at the magnitude of the velocity in the x direction for the ball rolling off the table. What do you notice? That's right! The magnitude is the same throughout the entire motion. Let's think about this. You roll a ball off the table. We know gravity is pulling the ball down faster in the y direction, but what's affecting the x direction? We're ignoring any drag that may be caused by air. There's no friction from the table to cause the ball to slow down, so nothing is causing the ball to slow down or move faster in the x direction until it hits the ground. Since nothing is changing the ball's velocity once it leaves the table, the magnitude remains the same throughout the entire motion. Now let's take a closer look at the velocity in the y direction. The result we see with the magnitude lengthening is expected because of the acceleration due to gravity. Last observation. Let's take a closer look again at the solid green arrows. Notice how the x and y vectors with the ball rolling off the table are the components for the solid green arrows. So the solid green arrows represent the velocity and the actual path of the ball, and the dashed lines represent the components for the resultant velocity vector. I lied. One more observation. Again, both balls are dropped at the same time. Notice how the velocity in the y direction occurs at the same time with the same magnitude in both situations. Here's another visual snapshot showing that both objects let go at the same time. Even though one is dropped and the other one has some velocity in the x direction, they both fall at the same rate in the y direction. Here's a diagram showing a ball launched at an angle from the ground. The solid green vector is the resultant velocity of the ball traveling, and the dashed line are its components. Notice how the velocity in the x direction stays the same throughout the entire motion. Then notice how the velocity in the y direction decreases when the ball travels up towards the maximum height. At the maximum height, the velocity in the y direction is 0. But remember, the velocity in the x direction is not 0. As the ball travels downward, the velocity in the y direction increases. Take a closer look at how the velocity in the y direction at the same height is equal but opposite direction. Another similar feature is the launch angle equals the landing angle. Now on to your favorite slide, how kinematic equations are applied in projectile motion. Since projectile motion is two dimensions, you have the kinematic equations for the x and y direction. However, the nice part is that the velocity in the y direction is constant. So what does that mean for the acceleration in the x direction? That's right, it's 0. So the kinematic equations are reduced, and you're really only left with x equals x naught plus vx naught t. What's similar between the kinematic equations in the x and y direction is the time. If you happen to calculate the time in the x direction, you can use that same value in the y direction. That's because the two velocity components in the x and y direction are traveling together. Now let's solve a couple of examples together. A tiger leaps horizontally from a 6.5 meter high rock with a speed of 3.5 meters per second. How far from the base of the rock will she land? Now press pause and try to solve this problem on your own. Alright, let's start with the givens. We're given that the initial height is 6.5 meters, the final height is 0. We can assume that the initial x0 is 0. We're given that the initial velocity in the x direction is 3.5 meters per second, and we know that velocity in the x direction remains constant, so the final velocity in the x direction is also 3.5 meters per second. And we want to figure out how far, meaning x. The correct equation to use is x equals x0 plus vx0 t. However, we don't know what the time is, and we want to solve for x. So in order to figure out what time is, we can use the kinematic equation in the y direction to solve for time, because it equals in both directions. So the first step is to cancel out anything that equals 0, and that reduces the equation. Then we know two negatives equal a positive, so that reduces down, and now we can solve for t. Once we solve for t, take the square root, and then plug and chug. And we get 1.15 seconds. Then we just plug that in to our x equation. We do that, and we get 5.25 meters as our answer. Alright, another example. Press pause and try to solve this on your own. A football is kicked at ground level with a speed of 18 meters per second at an angle of 35 degrees to the horizontal. How much later does it hit the ground? Here's our givens. Velocity is 18 meters per second at 35 degrees, and we want to find time. It's best to draw a picture for this problem so that we can see the direction of the ball and at the correct angle. However, in order to use the kinematic equations, we need its components in the x direction and y direction. To solve for the components, we just use trigonometry. So in trigonometry, we get the initial velocity in the x and the initial velocity in the y. In x, it's 18 times cosine 35, which equals 14.7 meters per second. And for the initial velocity in the y, it's 18 times sine 35 equals 10.3 meters per second. Now we're ready to figure out which kinematic equation to use. Oh yes, and we can also assume that the initial height is 0, the final height is 0, and the x0 is 0. Alright, so I always like to start with the simplest equation and see if that one works. However, we don't know x or time, so that means we have to pick a more complicated equation. So let's do this one. Now we can solve for time. Cancel anything that equals 0, rearrange the equation, two negatives equal a positive, and we can cancel time. So that reduces our equation to this. And now we can solve for time. Ta-da! Now all we have to do is plug and chug, and we get 2.1 seconds. Have a good night.